Okay, so as I mentioned before, we're going to skip the second law for now. Okay, the second law will be something where we address it in when we talk about problem solving. Okay, so it's going to, in fact, College Board makes its own little topic inside Unit 2 of dynamics and kinematics. And so what happens with third law? Okay, so the amazing thing about force is that they in nature they exist as pairs. Okay, so if I have one force exerted on an object, I've got another force exerted in kind of in the opposite direction. Okay, so we have this. We keep talking about this word interaction, right? So when we talk about interaction, it means there has to be two things affecting each other. Okay, and so Newton's third law of motion. Okay. States that for every action force, okay, there is an equal but opposite reaction force. Okay. So really I like to call this Newton's golden rule. Okay. Because I don't know how many times you've heard, an adult tell you, right, for every action there's an equal but opposite reaction. Well, that's based on Newton's law of motion, and what happens is they leave out the word force, right? So anytime you leave out the word force and you make that statement, you're doing the golden rule, right? You're doing the life lesson. In fact, if a teacher says, for every action, there's an equal but opposite reaction. It says that's Newton's third law. They're actually incorrect because his law states that word force. Okay, so the way we think about it is that equal, right? So this is dealing with our magnitude, right? Our size, and this is our direction, the opposite part. Okay, so what we're saying has an equal size, but it's opposite direction. Okay, and these forces, or this pair of forces, what we call action-reaction pair. Okay, or action-reaction forces. Okay. So easy way to think about this. I got a little picture over here off to the right with the hand on it. So the way these work is if I exert a force on the wall, well, the wall, right, then the wall exerts a force on me. Okay, and that's what's happening here. So I'm pushing on the wall, right? And so what is the wall doing back? It's pushing on me, right? Or simply put, F of hand on wall equals negative F of wall on hand. Okay? And so this would be my F of, wall on hand, and this is my F of hand on wall. You basically just flip those, right? So the way it's generally written is F of A on B is equal to negative F of B on A. Okay? And you just kind of you replace your A and your B with what's happening, right? So I got A is hand, B is wall. Well, then I flip them. Wall is hand, or wall is B, and A is hand. Okay? Now, one thing to note in our scenario, if we're kind of working on this hand on wall on hand scenario, is that they're not going to cancel out. Okay? Yes, in the grand scheme of things, if I were to kind of place my system as, got a little too close to the scroll bar here. So if I were to hit it again, I will learn this time and kind of shorten up what I'm trying to do here. So if I place my system around the whole thing, yeah, now those two forces are internal. But that's not Newton's third law. Newton's third law now treats the two systems as separate systems, or the two objects as separate systems. Okay, so the red dotted line would be the wall system, and note that my hand's force on the wall is external to that, And then the blue would be my hand, right, or the hand system. And now note that the blue arrow, the blue force, is now external to that, okay? And so that's why they don't cancel out. Now, in the grand scheme of the universe, yes, ultimately they do cancel out, because if we look at the universe as a whole, those two forces are internal and they're not going to affect the motion, right? Because, yeah, they're going to be equal in size and opposite in direction, okay? Now let's just look at a couple questions here. The first question would almost certainly be more of a multiple choice question. All right, so while driving on a road, a firefly strikes the windshield of a bus and makes a quite obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The firefly hit the bus and the bus hits the firefly. Now, which of the two forces is greater? The force on the flyer that the firefly experiences, or the force that the bus experiences? Okay, so really this is a trick question. And the reason why it's a trick question is because the force is equal, right? Newton's third law tells us, right, that the force of the bus on the firefly is equal in size but opposite in direction. Okay? And so they're equal to each other, right? So the magnitude of the forces are going to be the same. Now, this is what's really different. Sorry about the bell. What's really different here is not, and we'll get into it when we talk about Newton's second law, it's not the force, but it's the acceleration, right? So, and that comes from the formula. I'll give you a quick preview of the second law formula. It's mass, right? F equals ma, okay? And so what happens if I look at the bus on the firefly, so my firefly has a little mass, which means it's going to be a big acceleration. And then my bus has a big mass, and it's going to be a small acceleration. Okay, but they're going to be equal, right? So the size of it, little m times big A, is going to be equal to big M times little a. Okay. Another question is this: if an object falls, right? So yeah, we understand that the object is being pulled towards the Earth, right? So F of Earth on object, right? But what happens is the Earth is actually getting pulled up by the object, so force of object on Earth, right? But here's the thing. Notice that my arrow that I drew for my Earth or my planet is still inside, okay? And that goes back to this idea over here of, yeah, so the little a for the Earth would be like a, right? So it'd be like big M times little a equals little m times giant A, right, type thing, okay? So that would be this scenario, right? So you wouldn't see that acceleration. But in fact, if you drop something, that object is actually pulling the Earth up, but not being accelerated at a very fast rate, okay? But again, this would be a multiple choice question, right? So it'd be like A, the firefly, B, the bus, C, not enough information, D, they're equal, right? Or something along those lines, okay? Now the next question, I have a couple typos, right? And so the first typo, really they're both the same typo. It shouldn't say a cat of mass 50 newtons, a cat of weight, right? 50 newtons in here, same thing. It should say a weight of 300 newtons, okay? So a cat of weight 50 newtons jumps on a dining table of weight 300 newtons. As the cat walks around on the table, what is the average force that the table applies to the cat? So here's my, right, I'm very artistic, as you can tell, right? So if the cat, right, and we know that the table has a weight, right, Fg of 300 newtons. We know the cat has a Fg of 50 newtons, okay? But here's the thing, this weight doesn't matter, right? We're only looking at what is the cat doing. So the cat is pushing down on the table, so force of cat on table, right, is 50 newtons. Well, what does the table have to push up with, right, onto the cat? Well, guess what? has to have a magnitude of 50 newtons, okay? So our answer would be choice E, right? Because essentially, again, if we look at systems, I've got the cat system, right? And then I have the table system. They have to be equal in size, but opposite in direction. Okay. The next video is we're going to start talking and shifting our thinking to problem solving by first looking at what are called free body diagrams.